Let's start. So now we have talk by Dr. Enrico Landi. Dr. Landi obtained both his graduate degree in astronomy at the University of Florence, Italy, in 1998. After 1 year postdoc at Max Planck Institute for Aeronomy at Katlenburg-Lindau, Germany, he worked at Naval Research Laboratory for 10 years until he joined the University of Michigan in 2010, where he is currently working. His research interests encompass solar and heliospheric physics, spectroscopy, and plasma diagnostic techniques, as well as atomic physics. So please go ahead, you have your 40 plus minutes.
Okay, thank you very much, Gregory, for the introduction and for allowing me to give this lecture. And without further ado, I would also like to all of you for tuning in and listening to me. So today we'll be talking about plasma diagnostics from optically thin plasmas. But since I work on solar physics, I will mostly talk about applications to the solar atmosphere. Now, why do we want to do any plasma diagnostics from the solar atmosphere? Essentially, because in this way we can actually measure the properties of the atmosphere itself. And what we want to know about these properties is pretty much, in a sense, anything that you can. You would like to know about thermostatus of the atmosphere, which is ion and electron temperatures, the electron density, and how the plasma is organized as a function of temperature. How much material do I have at every single temperature? Then I would also like to know about its dynamical status. Bulk motions, whether the plasma is moving towards me or away from me. Non-thermal motions, which are all motions that are not described by the ion and electron temperatures. And then I would also like to know about the composition of the solar atmosphere. That's because this is a very important parameter about the plasma in general and about the solar atmosphere in particular. And also I would like to know about how the plasma is ionized. And this is very important because the charged states, the ion abundances, are then eventually measured in situ by probes that measure the properties of the solar wind anywhere in the heliosphere. And then, last but not least, I would like to measure and to know something about the real player, the real ruler of the solar atmosphere, which is the magnetic field. So these and many other properties is something that I would like to know. And in order to study them on the sun, we need to utilize techniques that use remote sensing, that use radiation in order to carry out these measurements. Now, to measure these things, there is a lot of stuff that can be used, and pretty much all wavelength ranges can be utilized successfully for measuring this or that particular property. So in order to describe them all, I would just need an entire semester to describe them all. So in this lecture, I will focus just on spectroscopic spectral line diagnostics utilizing extreme ultraviolet spectral lines. And I chose that because this is at the moment the main tool that we have at our disposal for studying the solar atmosphere. And I will neglect the continuum emission, which also is very important, as well as all the other wavelength ranges. And a lot of what I'm going to say today can also anyway apply to the X-rays. So first of all, in order to make you understand how to use certain plasma diagnostic techniques, I organize the lecture in two parts. The first one will tell us about the basics of line formation mechanisms, because in order to know how to use a particular diagnostic technique, it's better to understand why you can use it in the first place so that you can also understand the limitations. And then I will describe a few of the most important diagnostic techniques that we use. Those that utilize line intensity ratios, those which are meant to measure the thermal structure of the plasma, which means, again, the distribution of the amount of material as a function of temperature. Then I will describe a few diagnostic techniques that utilize the line width. And then, eventually, I will talk about ways of measuring the ion temperatures. And then eventually one nice technique to measure the solar wind speed. And I chose to add this one because with the launch of the new probes, Solar Probe Plus and the Parker Solar Probe and the Solar Orbiter, there will be more and more interest in connecting observations from remote in the Sun to observations in situ made by these new probes. In all of this, I will neglect diagnostic techniques that measure actually again the most important part of the solar atmosphere, which is the magnetic field. This is a pity because we have new instrumentation, DKIS, and the less known upgraded COMP, which will provide measurements of the magnetic field in the solar corona. But to describe these techniques, it's an entire lecture in and of itself, so I will skip on that. So, without any further ado, let's go and look at how spectral lines are made and how they are formed. Now, in these two panels, on the left panel, you have a spectrum observed by the ISO spectrometer on board the Japanese satellite Hinode, which shows a few lines between 188 and 191 angstroms. And all of these lines are emitted by individual ions. Now, for each of these lines, the intensity as a function of wavelength is distributed very unevenly, and you have peaks where the intensity is maximum, and then the intensity decreases very quickly. Each of these profiles for each of these lines can be approximated in the solar corona, and I will not be discussing why, can be approximated with a Gaussian function. So in order to measure the properties of this spectral line, all I need to do is actually fit a Gaussian to each of and every one of these spectral lines. And even if the lines are not very well separated, like those at 190 angstroms, there are programs that can disentangle the two and provide the parameters of each of these lines. Now, what are these parameters? First of all, we have the line width. The line width is measured as the full width half maximum, which is the width of the profile at a height which is half of the peak of the line. Then we have the line centroid, which is the wavelength at which the peak of the line is found. And then eventually we have the line flux or intensity, depending on the units. And this is given by the area below the spectral line profile. And each of these quantities gives us precise information about the plasma. As an example here, we have an image taken by the eye spectrometer of the solar region of the limb, scanning the slit of the spectrometer over the entire area. And you can see with the line intensity, you see a pretty picture of what this active region, for example, with all the loops look like. And this is done with line intensity. And as we will see in a second, it allows us to measure a lot of plasma parameters. But also, you can do the same map with a line centroid, because at every single pixel you have a spectral line profile for which I will have measured both the centroid and the width. And with the centroid, what it tells you is that through the Doppler effect, whose formula is just written there at the bottom, you can measure the line of sight bulk speed of the plasma. And because if the plasma is moving away from me, the wavelength will be longer, and here it is marked as red. Or if it is moving towards me, collectively, the wavelength will be shorter, and here it is marked in blue. So from not only see how the region is made, but I also see how the plasma is moving. And then I can do the same with the line width. And with the line width, I can have information about two things, and we will get back to that later in this lecture. I can measure non-thermodynamics, which means all the dynamics which cannot be resolved by the spectrometer as is not caused by thermal movements of the emitters of the ions. And also, I can measure the ion temperatures using the formula there at the bottom. But we will go back to this formula later. But anyway, you can see that, for example, these loops, these bright kinks that you see at the solar limb, they have a very peculiar distribution of the line width, with the line being much broader at the loop top than in the loop body, and then all the loops are much wider, have much wider spectral width than the rest of the sun. Now, we discussed how to use centroids and line widths. How do you use line intensities? Well, you can use them to do a lot of things. You can measure the electron density and temperature. You can measure the plasma thermal structure, again, how the plasma is structured in terms of how much material I have at every temperature. And then I can measure the element abundances, the composition of the plasma. Plus, if I can measure the polarization of the spectral line, I can measure the magnetic field, or at least part of it, and I will not be dwelling on this. And then I can use also some more exotic techniques, which are absorption techniques, whereby I can measure the properties of the absorbing plasma, techniques for simultaneous diagnostics, and I can also use them for empirical modeling. In a sense, the intensity is kind of the queen of the properties with which we do measurements, but also the others are important. Now, how does the intensity get formed? And this is very important to understand how I will use it for diagnostic purposes. And first of all, if I consider a little volume in the solar atmosphere which is emitting, the power that this volume emits in all directions isotropically is given by the simple product of the total number of emitters, which is given by the density of the emitters, Nj, times the little volume, and then the probability that this emitter will actually make a transition, a radiative transition, that emits the photon. Now, this is for the little volume, but then if I'm observing the sun, I'm observing across an entire line of sight. This is where the first great assumption of this line of trade takes place. We assume that the plasma is actually optically thin. Optically thin means that once the radiation is emitted locally, it can travel all the way to my instrument without interacting with the plasma in front of it. And this means that what I observe eventually will be just the sum of every single emission of every single volume along the line of sight. And so I can express that with this simple integral. Now, what is very important, the most important quantity in this integral is the number density of the emitter, because this is where there is the physics that rules the process of light formation. Now, with some little tricks, multiplying and divide by several different quantities, I can express this number density of emitters as a product of 5 different terms. The first of these terms is the level population. This is the ratio between the total density of the emitters at the upper in the energy level where the emission that gives rise to the spectral line originates from, relative to the total amount of ions that I have in my plasma. The second one is the ion population. How many of the nuclei which belong to the element X, how many of them are there in the charge state in the ionization level plus M, which is emitting my line. This is called the charge state composition, and this is what in situ instruments measure when they measure the solar wind. Next, I have the element abundance, the ratio of the total density of my element X divided the total density of hydrogen. And we use hydrogen because hydrogen is by far the most important element in the solar atmosphere. And just as for information, we call even absolute abundance the abundance of any element relative to hydrogen, or the other abundance of element X relative to Y as the so-called relative abundances. Then you have the ratio between the total amount of hydrogen divided the electron density, which we will discuss in a second. And then eventually I have the electron density itself. So my emission will be proportional to the electron density directly, plus any other dependence that we will discuss now. Now, each of these terms is very important for light formation, and is our gateway to measure plasma properties. First of all, you have the level population, the ratio of the total of the ions in the upper level J relative to the total amount of ions that I have. This depends on the electron density and temperature, and so I can use it to measure those two quantities. Then I have the ion fraction, the ratio between the total number of ions to the total number of the elements. This is used for thermostructure diagnostics. Then I have the element abundance, which I can use for measuring the element abundances. And then eventually I have this term, the ratio between hydrogen and free electron, which is a function of the electron temperature, but only for temperature below 100,000 Kelvin, and we will discuss why in a second. And then I will have the electron density, and this gives us the reason why, in a sense, denser plasma will normally emit more. Now, how do the emission is generated? How is a spectral line generated in the first place? Because this is why we can understand why each of these terms can provide us information about the plasma. So here is the simplified atomic model. We all know that if I have an ion in a plasma and this ion is undisturbed, this ion will have its own energy at the lowest energy of all, and will stay there forever. However, if this ion gets perturbed, it can change its energy. And it can only assume discrete values of the energy, and each of these are called these excited energy levels. Once the ion has reached this excited energy level, it is unstable and will tend to make, more or less quickly, a transition to a lower level, be it the ground or another excited level. And this transition is what generates the photon that becomes my spectral line, because it emits a photon. And the same ion can produce many spectral lines depending on how many energy levels it has. So the whole thing about understanding how a spectral line is formed is how do I get the ion in and out an excited state. And in the solar atmosphere, there are two ways to do it, which then determine the level of population, which is the parameter we are studying now. There are electron-ion inelastic collisions. Elastic collisions don't change anything. You really need collisions in which the incoming electron changes its energy, and in doing so changes the energy of the ion. And also you can have photoexcitation. For the time being, we will neglect photoexcitation. It is important for the last technique, but we will neglect it for the time being. Now, in order to calculate the level of population of a single level, the one that emits my line, I need to take into account all the collisions and that take place and all the radiative decays that take place in and out of this level. In doing so, we make one assumption. Since the electron-ion collisions are extremely fast processes, they're normally faster than anything that happens in the sun, meaning that at any given time, I can assume that they are in equilibrium. I have enough excitation as I have the excitation. And so the total number of transitions or processes that populate my level will be equal to the total ones that depopulate my level. And this is the equations that we need to solve. For every level, I have this equation in and out, and then eventually we have a normalization condition. For each for the processes that populate my level, I have collisional excitation from higher levels, collisional excitation from lower levels, and then cascade from higher levels, basically radiative transition from excited level down to my level. And then I have the same processes going out of my level. And what creates my spectral line is the very last one of this term, the cascades to lower level. This is the line that I'm interested in. And we need to solve this system and to calculate, in order to calculate the level of population. But what is very important to notice about that? That first of all, that the electron density determines the number of electron-ion collisions. This means that this level of population will be dependent on the electron density. Second, the electron temperature determines the value of the collision rates that we have, meaning that the level of populations will depend on the collision on temperature as well. This is why this term depends on the electron density and temperature. Now, moving on to the ion population, these are determined by all the ionization and recombination coming into the level and then those leaving the level. And so the fundamental equation is actually given by that needs to take into account them. And these are electron-ion collisions, which can ionize and recombine an ion, and also photoionization. And if you take both of them into account, you have an equation like this. And this equation tells you that the change over time of the total abundance of this ion is given by all the transition that creates my ion, recombination into this ion, ionization into this ion, plus photoionization from lower ions into this one, plus those that destroy my ion, which are exactly the same processes but originating from this ion. And there are several different possible processes. As you can see, there are several alpha coefficients, each of them being important. Now, this is a system of equations which is normally used to calculate the charge state of evolution of solar wind, of flares, of anything where the plasma properties change slow enough to be affecting significantly the ion population. What we do in the solar corona, though, assuming that its evolution is very slow, is to assume two things. First of all, that the plasma is in ionization equilibrium, meaning that it doesn't change in time. And this is normally true if you have a slowly evolving plasma. And second, that we don't have photoionization. If you accept that, what you have is the following equation, where the derivative is zero, of course, and the photoionization terms go away. And then you have the normalization condition. What you can see from this equation is that both the destruction and creation terms both depend on the electron density in the same way, meaning that the electron density can be factored away. So what happens is that the ion fraction don't depend on the electron density anymore, not on time, not on electron density. What they do depend upon are the electron temperature, because each of these four collision rates that for ionization and recombination are very, very strong temperature dependent. Now, since it doesn't change with time, the ion population can be calculated once and for all. And here is an example. For oxygen, if I have low temperatures below 10,000 Kelvin, everything is in neutral. I don't have any ionization. As I start to heat the plasma, oxygen 1 gets ionized very quickly in the form of oxygen 2, and so on and so forth. This tells you two things. First of all, that I can calculate these things beforehand if I have the data to do that. Second, every ion is formed in a very narrow temperature range. This means that in order to study a certain region of the corona, I have to use certain particular ions. Say I want to study the 1 million degree corona, I have to try to observe oxygen 7. Otherwise, I won't be seeing anything. And also, different ions provide, if I observe many ions of the same element, I can sample different plasmas. So, this is for the ion balance. Then we have the element abundance. For a given plasma, we can assume that the element abundance is a constant, or if it evolves very slowly with time. However, along the line of sight, if I have different plasmas, one after the other, they may have a different composition, and this can be a problem. And one thing why we are interested in the composition is that the photospheres of the corona have a different composition. This is called the Fitt effect, and we will get back to that later. And it is so important that actually in this webinar series, Dr. Martin Laming gave an entire lecture on it that I strongly urge you to look at, because it's very well made and very interesting. Next, there is the other term, which is the ratio between free electrons and total hydrogen. Now, this, in the solar corona, this ratio is constant, and that's because in the solar corona, all hydrogen and helium, which constitute 99.9% of the plasma, are actually totally ionized. So even if I ionize more other elements, the total amount of electrons they will add is negligible. So this ratio is constant. It becomes temperature dependent only at very low temperature, 30,000 degrees or less, when ion and helium are only partially ionized. So temperature means I can ionize them more or less, and so I have more or less electrons available. But for the diagnostics of the transition region and the corona, this number is just constant. So we have discussed now each of these terms. How do we use them for plasma diagnostics? To do that, we have first to define two new quantities. The first one takes the level populations and adds a little bit more atomic physics term to define the contribution function. You may recognize the first four factors are actually the same as in the level population. Plus I have the other atomic physics constants, the frequency or wavelength of the radiation, and the Einstein coefficient. Then I have the so-called differential emission measure. And if you do the simple math, you find that the flux or intensity of the line takes this simple property. Basically, is the integral of the product of the contribution function and the differential emission measure. Why am I doing that? First of all, because the contribution function describes all the atomic physics involved in the process of line formation. And this atomic physics is known so that I can calculate this quantity beforehand, before doing anything. And if you have a special code like Chianti, you can do that for free and be ready for your diagnostics. The differential emission measure instead is the quantity that we use to describe how the plasma is distributed in temperature. And so this is something we want to measure. And also defining the DEM like that, the differential emission measure like this, changes the definition of the integral from volume to temperature. So now I'm counting essentially the contribution of a spectral line at every temperature range. Now, how do I use this for spectroscopic diagnostics? There are several techniques, and now we're going over them. The first and the easiest of them is the line intensity ratio. I take two lines that I measure with the spectrometer, and I do the ratio between the intensities or the fluxes that I measure. This is the most popular technique of all of them because it's fast and easy. But if you look to the equations that I gave you before, if the lines are emitted more or less in the same temperature range, this ratio is proportional to the ratio of the contribution functions that I know beforehand. Now, who are these lines that I'm going to use? I have several choices. The first one is to use lines from the same ion. And if I use them, the ion abundance will be the same because the ion is the same. The element abundance is the same. So this ratio will be just a function of the proportional to the ratio of the level populations. So it will be a function of density and temperature only. Or I can use lines from the same element but different ions. So to the dependence of the previous ratio, I'm adding the dependence on the ratio of ions, of the ion abundances, which is, as we have seen, a very strong function of temperature. Or I can even choose two lines of different elements. In doing it, so I'm adding to the previous two dependencies also the dependence of the element abundance. And this is the ratio we'll use for measuring the element abundance. So let's review that. If I use intensities of lines from the same ion, they can be used both for measuring the temperature and the density because, as we have seen, the populations are a function of these two quantities. So depending on which line pair I select, I can measure either the electron density on one side or the electron temperature on the other. And so here are a couple of examples, and I can have a factor of 5 or even more of change of the ratio between as a function of the electron density or the electron temperature that I want. And what is nice about that is that these ratios are independent of the ions and of the element abundances, so their uncertainty is less. And this means that this explains their popularity. They are by far the most used diagnostic tools that we have. Also, since in a spectrum normally I have several lines, there are many, many lines to choose from. And this is very important because in this way, even if I take lines utilize different ions consecutively, and for each ion I take a ratio, I can measure the density or the temperature in several different temperature ranges. So I can start building a picture of this plasma, which is much better than if I use just one line. Then, if I use lines from different ions. Now, we have seen that each ion, because of the ion abundance, is formed in a temperature range. So its emission in the left panel, I took here as an example two ions from iron 12 and iron 13, which are very popular in the solar corona. They're just formed at a slightly different temperature range, iron 12 being a little bit colder than 13. If you take the ratio of their line intensities, you can see on the right what the ratio looks like. As I increase the temperature, this ratio increases like crazy. And you can see if I took lines from the same ion, the factor of change of the ratio between the temperature range was around 5, 10-ish. Here it's 4 orders of magnitude. It's a very powerful temperature diagnostics. So what I can do with it, if I take consecutive ions, they provide excellent temperature diagnostics. And also, the element abundance is not a problem for this one. However, there are some cons for this type of ratios. First of all, that I'm adding uncertainties in the ionization and recombination rates that are used to calculate the ion fractions. Also, since the ions are formed at different temperature ranges, there is the risk that my ions are actually formed by different plasmas with almost isothermal, each at a different temperature. So I'm kind of mixing the information here. Furthermore, I can have problems with density. I need to know density beforehand in order to get the ratio. Or I can choose lines which are not density sensitive, and there are some. Now, this is for the ratio for lines from different ions. If I take lines from different elements, this is the prime tool for measuring the element abundance. And they're great for studying the Fippe effect. Now, what is the Fippe effect? Again, I urge you to go and look at Martin's webinar because it's very nice. But essentially, the Fippe effect consists of the fact that the abundances in the corona are different from those in the photosphere. And if you define the Fippe bias as the ratio of the abundance of an element in the corona to the abundance that it has in the photosphere, this ratio looks like that. If I plot it as a function of the first ionization potential, the Fippe of the ion, about 10 electron volts, sulfur, oxygen, carbon, and so on, it's essentially constant. It's 1. You have the same composition. For elements lower than with Fippe lower than 10, I have an enhancement which goes from a factor of 2 to a factor of 4. Why is that? We don't know, and it's very important because, as you see in Martin's lecture, this is tied to the presence of alpha waves which accelerate preferentially low Fippe ions over high Fippe ions. And this is important because alpha waves are the main suspect for heating the solar corona, accelerating the solar wind. And so this is just another manifestation of the same physical process, which is very important to measure. However, this is very important, but it has its own drawbacks. First of all, in order to utilize this ratio, I need to know the plasma temperature and density beforehand because I'm using different ions from different elements, which might be different depending also on the electron density. So it's very important to know them before. But in order to measure the abundances sensibly, with measurements that make sense, I need to use ions of different elements which are formed at the same temperature range. Because otherwise, if I have along the line of sight different plasma at different temperatures, I might measure the abundance of relative abundance of one plasma relative to the other, but in terms of the physics of the Fippe, this really doesn't mean very much. So I really need to be careful here. Now, these techniques utilize line intensity ratios. Now we move on to a different type of techniques, those that utilize simple line intensities, not ratios, to measure the thermal structure of the plasma. In order to understand that, we need to go back to the original equation for the line intensity. And we can do two different cases here. The first one, if the plasma along the line of sight is nearly isothermal. And this happens in the solar corona when it is observed off the limb. If you don't have active regions or anything, normally the plasma is very close to isothermal. In this case, I can express the intensity with an integral over the volume. And if the plasma is isothermal, and I choose lines who do not depend on the electron density, the contribution function is constant, and I can take it out of the integral, meaning that the line intensity now becomes something which is given by the simple product of the contribution function calculated at the temperature of the plasma, T of PL, and then density is not important because I selected a line which doesn't depend on the electron density. And this is times the so-called emission measure, which is a measure of the total amount of material that I have along the line of sight, regardless of its temperature. How do I use that to measure plasma properties? Well, there is a technique, which is the emission measure technique, which essentially consists of calculating a new function. An emission measure function is a function of the electron temperature, which is the ratio between the flux of the intensity that I measure on the line, which is F, divided the contribution function calculated as a function of the electron temperature for that very line. If you use the equation above, this new function, the m of Te, is given by the product of the emission measure, which is the same regardless of any line that I use, because it's a plasma property, times the ratio between the contribution function at the plasma temperature, at the real plasma temperature, divided the contribution function as a function of all temperatures. If I do that for many lines and plot all of them as a function of temperature in the same plot, this is what happens. Each of these curves is one of these EM of T curves for every single line that I chose. All of them more or less cross in the same position in temperature at the same height, which gives you the emission measure. So the crossing point, which is marked here with the horizontal and vertical lines, gives you the electron temperature and its uncertainty in the temperature, and the Y gives you the value of the emission measure. And you can see this works in the quiet sun above and in the corona hole below if you don't have any structuring along the line of sight. And also, this does not work at all if the plasma is not isothermal. So this technique also gives you a test of whether the plasma is really isothermal or not. And it's a very powerful technique. Now, if my plasma is not isothermal, I have to do something. But at this point, I cannot use this simplified version. I will have to go and use the real flux, the real expression of the flux. And what I need to measure is actually the differential emission measure. And the differential emission measure phi of t looks like this. If I'm looking at the limb and I don't have an isothermal plasma, I have normally a plasma which has a peak at a certain temperature, and then the dm goes down quickly at both sides. If I'm looking at disk plasmas instead, when I go towards lower temperature, I start to hit the plateau, which is the transition region, and then it goes even up. How do I determine this dm? Well, there are several methods. The main three being iterative techniques. I take whatever initial the differential emission measure function, and then iteratively I start to modify it, use it, feed it in the equation for the intensity, calculate the intensities that I expect from the DEM, and compare them with observations. And from the comparison of observation and prediction, I can see where the DEM is wrong, and so start iteratively to modify it to get the final one, which is the best one that reproduces the best of the observed line intensities. Or you can have inversion techniques. Now, inversion techniques take the integral above and really invert it, because in this integral you may note that I know the contribution function beforehand, the g of n and t. I measure the flux, so what I need is the phi function inside the integral. And there are techniques to determine that. And then there are the Monte Carlo techniques. These are brute force technique where I just start to change randomly an initial differential emission measure curve until the best one is found that reproduces the best of my line intensities. I'm not going into the detail of each of these techniques because, again, I would need 2 or 3 lectures to do that. But I want to highlight 2 main problems of these techniques. First of all, the solution that they provide is not unique. And this is due to the fact that this problem, getting the phi function inside the integral from a bunch of measurements, is actually ill-posed, meaning that I cannot really determine it uniquely because the integral eventually is just a sum of several different contributions. I can, in principle, have many different cases of along the line of sight that will be giving me the same final flux. I can minimize this problem by using as many ions as I can to get as much information as I can along the line of sight, but still the non-uniqueness persists. Second, as you can see, the temperature ranges over which this DEM is defined is very wide, meaning that I need to have many different ions available to do a meaningful measurement. So I really need spectroscopic observations with many different ions from the same or different elements in order to carry out this measurement. And also, as you can see in the disk plasma plot down at the bottom, several different elements are used. This means that this DEM is also prone to uncertainties to the abundance of the plasmas. And this is another problem. Now, this is for the line the thermal structure diagnostics. And all these techniques that I've talked so far utilize line intensities. What happens if I want to use the line width? Now, we may recall that the line width is given by such a question, and it depends on 2 different parameters. The first of all, T ion, describes the thermal motions, and the parameter is T ion, the ion temperature. And this gives me basically an indication of how much random thermal motion I have along the line of sight, whereby the Doppler shift changes the frequency of the line very fast, in way that I can't resolve. So the line gets broadened, and this parameter tells me how much is broadened because of this. The second one are the so-called non-thermal motions. These are any motion that I cannot resolve with my spectrometer, either because they're too small in size or because they're too fast in time, and my spectrometer cannot keep up. It can be rotation, oscillation from waves, turbulence, explosive motions, anything. And these are normally described with this value, with this parameter, the non-thermal speed. Now, you may notice one thing here, which is the fundamental problem of a line with diagnostics. I have two unknowns, both the ion temperature and the non-thermal velocity, in one single observable. And this normally spells trouble. Now, how do I deal with this? There are three ways that I can do, all of which provide some sensible results. First of all, I decide, okay, I give up knowing which of the two and how much of each of these two parameters contributes to the full width maximum. And I measure an effective velocity, which is just a velocity that is the sum of these two terms. I give up knowing more, but just determine this effective velocity. You may ask, what do I do with this parameter? I mean, I don't know who is who inside this measurement. Well, there is physics you can do. An example is here given by a paper done by Michael Hahn, where they measure the effective velocity as a function of height in a coronal hole for several lines observed by eyes. And they compare them with the expected value these widths should have if I have undamped alpha waves propagating in the coronal hole. And as you can see, at low heights, the effective velocity matches nicely predictions, but then they go down. And this going down of the effective velocity, regardless who was responsible, was interpreted as the damping of these alpha waves, whereby the energy of this alpha wave were given to the plasma and heated it. And they estimated that the plasma was hot, the energy dumped into the plasma was enough to heat the entire corona hole. So this was a great indication that alpha waves could heat the solar corona, and it's a testament on what this type of method can give you. But say, okay, I'm not satisfied. I want to measure either the ion temperature or the non-thermal velocities. At this point, the second best solution is to make some assumption. So, if I want to know the non-thermal speed, I make an assumption on the ion temperature. And the most common one is to assume that it is equal to the electron temperature. And this assumption works if the plasma is dense enough that you are near equilibrium. Or, if I want to know the ion temperature, I assume whatever value of the non-thermal speed, and I pick the one I like most. Problem with these two techniques is that these assumptions are not always justified. So I might be in trouble and get results which do not mean very much. So the third method is actually been developed by Tu et al., Professor Tu and collaborators in 1998. First, they noticed that I can determine upper limits to both these quantities because both of them cannot be smaller than 0. So, for example, if I set the non-thermal velocity to 0, I know that the ion temperature has to be lower than the value that I get when the non-thermal velocity is 0. Same way, if I set the ion temperature to 0, the maximum value of the non-thermal velocity is that value, and so my non-thermal velocity needs to be lower than that. This is without any assumption. The assumption comes here. I assume that the non-thermal velocity is the same for all the ions. What this means is that I can choose the smallest of the non-thermal velocities that I determine, assuming that the ion temperature is 0, among all the lines I got. And the non-thermal velocity of all these lines needs to be smaller than that value. But that limit tells me that the ion temperature needs to be larger than the value I get utilizing this non-thermal velocity. So, with the step 1, I determine an upper value of the ion temperature. With this term, I determine a lower value of the ion temperature. So I determine the range of temperatures of my ion temperatures. And this gives me a measurement. Here are a couple of examples. These are ion temperature from many ions compared to the electron temperature, which is the horizontal line with uncertainties, taken over a streamer in 3 different phases of the solar cycle. You can see that for a streamer, all the ion temperature are kind of close to the electron temperature on the high side, and they're pretty much constant regardless of the ion. If you do the same with a corona hole, this corona hole, you see that if I plot these ion temperature values as a function of the charge to mass ratio, They are all higher than the electron temperature, again, the horizontal lines, and also they depend on the charge to mass ratio. And this is an indication of wave heating. At least it's one of the observables for wave heating that we have. And so we can start doing models on how wave heating can provide me a model like that. Now, and time is almost up, I would like to briefly mention the last diagnostic technique, the one about solar wind speed. This is the so-called Doppler dimming technique, very popular with UVCS instrument on board SOHO, whereby I use the observations of the intensity ratio between two oxygen-6 lines, 1031 to 1037. And observed high up in the corona, they have the profile, which is given by the top plot on the left. The beauty of this ratio is that it's totally constant. If the density is high, this ratio is 2. If the density is very low, so that photo excitation is actually dominant, this ratio is 4. And it doesn't depend on density, and of course not on temperature. Now, if the density is very low higher up, where the solar wind is accelerating, the photo excitation for these lines is done by the emission in these lines emitted by closer to the sun. And if I don't have any velocity, you see that the 1031 line is photoexcited by the line on the bottom plot, and the 1037 line is photoexcited by the same oxygen-6 line, plus other two, which are carbon-2 lines. Now, the trick goes if I start to have a velocity. If I start to have a velocity, say, 100 kilometers per second, if I am the solar wind, and I'm accelerating away from the sun, I see the sun moving away from me. The spectrum gets redshifted and its wavelength moves towards the right, meaning that 1031 will be photoexcited less because I will have less ion in the profiles to absorb it, while the 1037 will lose photons from the oxygen-6 line, but will add photons for photoexcitation from the two carbon lines. And the more I go, the more this happens, to the point at a high velocity, I have the spectral line, which is and the 1031 is very little photoexcited, while the other one, the 1037, is still photoexcited. If I plot this as a function of speed, this is how the ratio looks like. Goes from almost 4, which is almost at rest, and decreases very quickly. And from the measurement of this ratio, I can measure the speed of the solar wind, which then I can match up to the values that I get at the with in situ instrumentation. And at this point, I stop here, and I thank you very much for bearing with me and listening to my lecture, and I welcome questions. Thank you very much.
Yes, thanks, Enrico. Very interesting and very clear presentation. Yeah, unfortunately, today we have a relatively light attendance, mainly because of racing meeting, where many of frequent participants participate, but I believe that this will increase number of online viewers of your recording in a while. So now we are open for question. Please unmute your microphone and ask question if you have any. I do see all microphone muted. I want to ask, could you just maybe very briefly comment on optically thick lines? What is fundamentally different and what can be learned with optically thick lines?
Well, optically thick line kind of invalidate most of these techniques because all these techniques rely on the fact that you can just simply sum up the intensity. So the best way to utilize them is doing radiative transfer, essentially make assumptions on the absorbing plasma and then see how the spectral line intensity and the profile emerge from this light. Having said that, there are techniques that do exactly that and allow to determine, for example, the electron temperature and the column density of the absorbing plasma by measuring how much light gets absorbed. And we developed one utilizing AIA data so that if you had a coronal mass ejection expanding, you could measure how the ejecta, which were initially cold from the erupting prominence, how much absorbed the background radiation. So you could see, for example, how much the temperature changed in this ejecta, and so you could then calculate how much ionization would change, and so on and so forth. So, or otherwise, you can start to make to try to determine at what height you do have absorption. Say, for example, you look at a spectrum from a wide wavelength range in the ultraviolet, you have both cold lines and hotter lines. Is looking at certain particular ratios that are supposed to have a fixed value, you can see how much the stronger line is decreased over the weaker lines. So there are the techniques that you can do to utilize optical thickness to your advantage, even if all that I talked to you so far, it cannot really be utilized for diagnostics anymore.
Okay, thank you. So do we have any other questions at the moment? So if you do, please unmute your microphone and then ask. Okay, given that all microphones are muted, I think that, and I believe everything or most of the point were David absolutely clear, and I really enjoyed the way how you have done so. So thank you very much, Enrica, and this all will be available online very soon. Thank you.
Okay, thank you very much.
Yeah.